Okay, so we've discussed the shapes of molecules when you have 8 electrons in their outer shell, and then you get 4 pairs, and that's the most common. We've discussed others where you have less than, it's not a complete outer shell, like an aluminium chloride and beryllium chloride. Now we need to talk about ones where the shapes where you can have more than 8 electrons. Right, so if you remember period 2, you can't, carbon, nitrogen, oxygen, fluorine, those atoms can't have more than 8 electrons in their outer shell because they're in period 2, and there's only room for 8 electrons. There's 2s2, 2p6. Whereas in period 3, you've got the d orbitals to think about. So it's not only 8 electrons; you can have more than 8 electrons. And principally, we're talking phosphorus, sulfur, and chlorine. But we'd also be interested in things like bromine and iodine, fairly common atoms. Okay, so let's look at one with 5 electrons then. 5 pairs of electrons, sorry. 5 pairs. So 5 pairs. A good example of that is PCl5, phosphorus pentachloride. Okay, so we draw a dot cross diagram of that. We don't really need to do it. This one is fairly simple, but I'll do it anyway. Right, so you've got phosphorus, 5 chlorines. Where they overlap, you have a dot and a cross, dot and a cross, dot and a cross, dot and a cross. So that is there are 5 electrons of phosphorus there, so there's no lone pairs. Right, now the way they're arranged, and of course the chlorines, I should put them in, but I'll just do one of them. It's got 6 more electrons that are not involved in the bond there. So I think it's easy if I draw a, this is supposed to be a flat piece of paper here. Okay, now what goes on that flat? You get phosphorus, and it is bonded to 3 chlorines. They're in the same plane, so that bit's trigonal planar really. All of those bond angles are 120, and then we've got 1 going up and 1 going down. Okay, so I'll put in the, so these bond angles on the piece of paper on the flat plane, they're 120 degrees, whereas these bond angles are actually 90 degrees. So it's a bit unusual that you get 2 bond angles. Everything else has only had 1 angle, 2 different ones here. And the shape of that is usually called bipyramidal. So, okay, so that's when you've got 5 pairs. Now let's see what you get when you get some lone pairs involved in that, and we'll just look at the most common one, and the AQA had a phase of always asking the shape of this molecule. I don't know whether they've lost interest in it or not now, but for a while, every past paper question was this. Let's see what happens. So we've got the compound, something like bromine trifluoride, which I couldn't tell you anything about, apart from the fact that there's asked a lot of questions on it, and the shape of it. Nothing else. So we could draw bromine. Now we've got 3 fluorines there. It is important to draw a dot cross diagram here for this one. So in the overlap, we have a dot and a cross, a dot and a cross, dot and a cross. Now bromine is in group 7. So it's got 7 electrons in its outer shell. I've only drawn 3, so there's 4 more, so that means there's 2 lone pairs there. Okay, and of course each fluorine, I'll just do it for 1, but they've got 6 more electrons there. We don't really worry about them. Okay, so that's the bromine we need to worry about. The center, what's the geometry around that? So we have got 3 bond pairs and 2 lone pairs. Now there are 2 different possibilities, 2 different answers which they'll accept for that. I think they're kind of like stereoisomers of each other, right? So we'll base our thing on this picture here, okay? So the one, let's do the first one is, so draw it a flat piece of paper again, and on that I'm going to have a bromine. And the one sticking up and sticking down, I'm going to draw in. Okay. And we'll have this one as a fluorine. So that means that these two bits, the bit I've got there and there, they're going to be lone pairs. So if I draw, that's supposed to be a lone pair there, and that's a lone pair as well. So the shape of this, you can see it looks like a T, and it is called it's called T-shaped. Now, what will those bond angles be? We'd expect them to be 90 degrees, wouldn't we? I should do them in red because I've been doing them in red all along. It's ever so slightly less than 90 degrees, though. Okay, just a little bit less than 90 degrees because those these you would expect those lone pairs to push the other one to repel a bit more and push the angle in a little bit. So the bond angle slightly less than 90 degrees. Right, that's one possibility. The other possibility is, I'll draw the flat thing again, is, and if you look in AQA mark schemes, they accept either of these. And it's, as I say, these questions are the only time you ever come across this molecule BRF3 or IF3 or ICL3, always that sort of thing. They all have the same dot cross diagram. They all have 3 bond pairs, 2 lone pairs. So let's put the bromine there. And this time we'll have all the fluorines on the flat plane. And of course, all the bond angles are going to be 120. Well, before I draw the bond angles in, you're going to have 2 lone pairs, aren't you? Let's do them in different colors. So you can have that lone pair there. That's going to push everything down, but then you've got another lone pair underneath, which is pushing everything up. So the shape would be trigonal planar, and the bond angles would be 120 degrees. They wouldn't be distorted because, as I say, one lone pair is pushing up and one lone pair is pushing down. So they're the 2 ones you need to know for when you've got 5 pairs. I wouldn't worry about when you've got 4 bond pairs and 1 lone pair. They don't generally ask about that. Right, let's look at when you've got 6 pairs. Right. So 6 pairs of electrons. And there we've got sulfur hexafluoride. Okay, so SF6. So dot cross diagram again, we could get away without drawing it. 1, 2, 3, 4, 5, 6. Sulfur there. Right, so we've got a dot and a cross in every single one. So sulfur's in group 6. So we've drawn all 6 of sulfur's electrons. There's none left over, so there's no lone pairs. And each fluorine, of course, was in group 7, so they would have 6 electrons. Okay, I'm only going to draw those 2. I'm not going to draw the whole lot. Be there forever. So let's think of the shape of that. Well, it's fairly similar to this thing here, right? Okay, except instead of having 3 on the blue plane, we're going to have 4 in a sort of a square. So let's do that. So here's my square, my plane, sorry, there's my flat plane. And my sulfur is going to sit in the middle of that, and it's forming 4 bonds to fluorines in a square shape, and each of those bond angles is going to be 90 degrees. And then we've got 1 sulfur sticking up, one fluorine sticking up, 1 fluorine sticking down. Those bond angles are 90 degrees. The ones in the flat plane, these are all 90 degrees, so every bond angle is 90 degrees. And so the shape is called octahedral, which is a bit confusing because octahedral sounds like there's 8 fluorines when there's only 6, but the reason why it's called an octahedron is those 6 fluorines are the corners of a regular octahedron. Okay, that's why it's called that. It's a bit confusing when you see it drawn on a piece of paper. If you have a model, it's quite obvious that you tend to think these 2 fluorines are different to the other 2, and they're not, because if you rotate the whole thing around, then they all end up in this. These end up in the square, and then 2 of the other ones end up sticking up and down. So they're all actually equivalent to each other. Unlike this one here, where those chlorines are not equivalent to each other. 3 of them are different to the other 2. But here they're all the same. Octahedral, bond angle 90 degrees. Now let's go on to what happens if you've got some lone pairs there. And again, you could have 5 bonding pairs, 1 lone pair, 4, and so on. But the only one they've ever asked, I don't think they've even asked this actually, but the only common one that you see written in textbooks and stuff is when you actually have 4 bonding pairs and 2 lone pairs. So a good example of that, interestingly for us, is xenon ZeF4, which is the first time you come across a noble gas compound. Xenon and krypton fairly readily form for a few different compounds. Argon forms a couple of compounds at incredibly low temperatures, near to absolute 0, I think. Helium and neon, I think they do form some interactions with other things, whether you call them compounds, and that's only at very, very low, like within 1 degree of absolute 0. But xenon and krypton form compounds. All right, so let's draw the dot cross diagram for that. So we've got xenon there, 4 fluorines, a dot and a cross, dot and a cross, dot and a cross, dot and a cross. Right, xenon is in the noble gases, so it's got 8 of its own electrons in the outer shell. I've drawn 4, so that means we've got 2 lone pairs left over, haven't we? Okay, so you can see it's 4 bonding pairs and 2 lone pairs. Another variation on that you can have, another variation on that is, which I've seen a few times, is, and I've only ever seen it, don't know what this thing is actually like, but I've seen it in relation to shape of molecule problems, is this ion, IF4 minus. So if we draw that here, oh, by the way, I should draw my fluorines there. Each fluorine has got, 6 other electrons, but I'm not going to bother drawing them all in. Here's iodine. And we've got 4 fluorines. Right, where they overlap, a dot and a cross, a dot and a cross, a dot and a cross, dot and a cross. So let's think about iodine. It's in group 7. I've drawn 4 electrons, so I've got to draw 3 more. But because it's IF minus, it's not just 3 more I draw 4 more. So I draw 1, 2, 3, and in red, this is the extra electron. It's pinched from somewhere else. There. All right, so you can see this is it's a so it's once again it's 4 bonding pairs and 2 lone pairs. So you can probably guess what's going to happen there. What happens is there's your flat plane. Let's put xenon in the middle of it. You've got 4 fluorines like that. So that means you've got 1 lone pair here above the plane and 1 lone pair below the plane. One's pushing up, one's pushing down. So the bond angles are an undistorted 90 degrees. And the shape of that is called square planar. Right, so we've done every single kind of possible shape that you need to know there. And just to summarize, here's the table. that we did last time, and now I've added to the bottom of that what happens when you get with 5. So you trigonal bipyramidal, then T-shaped when you've got 3 bond pairs and 2 lone pairs, or the trigonal planar version of it there. And finally, the one we've just done now. Oh, the one I haven't completed the table, but we don't really need that, do we? Because we've got it already. So what I'll do is I'll reduce that so you can see the whole thing, and then freeze the video if you want to have a look at that all in the same place. Sometimes quite nice to do that. See it all in one place. Try and squash it down so it all fits in. Right, that's about as good as best I can do. Okay, so the next video we'll do some more, see what happens when we've got double bonds. What does that do to the shape? Okay.